Hey everybody, Matt Morgan here. In this lesson, we're going to talk about electron pair geometries from OpenStack section 7.6. We'll go over a little bit about what we've learned so far about bonding and Lewis structures. We'll talk about why it's important to know the shape of a molecule. We'll talk about VSEPR, valence shell electron pair repulsion, and then go over the various electron pair geometries. So far, we found the valence electrons in atoms, where they are. We've seen how these electrons make bonds, both ionic and covalent bonds. The Lewis structures show us the arrangement and the kind of bonds that exist in a molecule. The Lewis structure by itself doesn't tell us the shape, but we can use the information from the Lewis structure to find a molecule's shape and bond angles. So why do we care about molecular shapes? Well, a molecule shape tells us a lot about what the molecule can do for us. Water dissolves many substances because it is a polar molecule. Water is polar because of its shape. One side is negative, the other side is partially positive. Molecules are shaped the way they are because electrons repel each other. That's the most important point over all the stuff we're about to go through. In fact, I'll say it again. Electrons repel each other. Electrons around a central atom of a molecule arrange themselves to be as far apart as possible. And that's how we get the shapes in the electron pair geometries. The system we use to find a molecule's geometry and its structure is called VSEPR. It sounds really complex. Valence shell electron pair repulsion. You don't have to memorize that phrase. You just have to be able to find electron pair geometries and molecular structures. And the name comes from the fact that electrons repel each other. So one of the challenging aspects of finding electron pair geometries and structures is that these are three-dimensional objects, and we're viewing them on a two-dimensional page in a textbook or a two-dimensional computer screen. But there are some visual tools that will help. And this is a good one, this PhET simulation. There's a link to the simulation in the Week 13 video folder. Use it and play with it and find that you can see and rotate the various structures and geometries. The simulation will be helpful after watching this video, but look at it again after looking at both the electron pair geometry and molecular structure videos and possibly even the homework video. So this term, electron pair geometry, used by the text, what this is, it depends on the total number of electron groups around a molecule's central atom, and we'll explain what that means. The electron pair geometry gives us the bond angles. So what do they mean by a region of high electron density? So an electron region can be a single bond, a double bond. A double bond is still a region of high electron density, triple bond, or a lone pair. So they don't just say electron pairs because it could be a single bond or a double bond or a triple bond. All of these things are one item used to define the electron pair geometry. Each of these is considered a region of high electron density. And these high electron density regions repel each other. So to find the geometry, start with the Lewis structure. You've got to have the correct Lewis structure to get the geometry. Review how to draw Lewis structures if you need to. We're going to assume you already know. Count the total number of electron regions around the central atom. Single bond, double bond, lone pair, etc. So here are the shapes associated with the number of electron pairs around a central atom. If we have two regions, the electron pair geometry is linear, and the bond angle is 180 degrees. Okay, here's a couple pictures of that. So two regions repel each other, they make a straight line. They're going to be on opposite sides of the central atom. Here's a 3D rotation of a linear molecule with two regions around the central atom. If we have three regions around the central atom, it makes a trigonal planar arrangement with 120-degree bond angles. There's a picture of the trigonal planar. There's a 3D rotation. Central atom, three regions adopting 120-degree trigonal planar arrangement. We see the three sides, we see the single plane. Four regions around a central molecule make a tetrahedral arrangement. Those bond angles are 109.5 degrees. There's a picture of the tetrahedral arrangement. There's a rotating 3D model. Five regions is a trigonal bipyramid. Now note those bond angles. There are two different sets of angles, 90 degrees between the equator and the axis and 120 degrees around the equator. And we'll show you what we mean by that. Notice between up and down and where it's rotating, that's 90 degrees. But if you look along that vertical axis, you see it's almost like a trigonal planar arrangement, 120 degrees. The combination of those is a trigonal bipyramid. Six electron regions is the octahedron. There's six regions around the central atom. It's called an octahedral because if you connected those lines, it would be an eight-sided solid. Here are pictures of both the trigonal bipyramid and the octahedron. Notice the three around the equator versus the four around the equator. There is our octahedral arrangement. All bond angles are 90 degrees with that. So here's table 7.16 from the textbook. It shows all the different arrangements of the number of regions around the central atom, the bond angles, and the name. So we've talked about molecular shapes, the VSEPR, why they're important, electron pair geometries, all the different combinations in our course. Next lesson, we'll go from electron pair geometry to molecular structure. There's my email. We have online office hours Tuesday and Thursday mornings, 9 to 10 a.m. And you can make an appointment if those times don't work for you.